when greater magnification is required to view microscopically smaller objects, a compound microscope is used. A compound microscope consists of two convex lenses arranged coaxially. The lens O that is close to the object to be viewed is called the objective, and the lens E that is close to the eye is called the eyepiece. The objective of a compound microscope is of a small focal length and has a small aperture, whereas the aperture of its eyepiece is large. Let a small object AB be placed at a distance that is just greater than the focal length of the objective FO. When the light rays from the object are incident on the objective forms an image A-B', which is real, inverted, and magnified. This image A-B' acts as the object for the eyepiece. If the position of the eyepiece E is so adjusted that A-B' lies between the optical center and the first principal focus, then a virtual and magnified final image A'-B' is formed. Let the height of the object AB be h and the height of the image A'-B' formed by the objective be h'. Let us also define the tube length L of a compound microscope as the distance between the second focal point of the objective and the first focal point of the eyepiece. If MO is the magnification due to the objective and theta is the angle that the ray refracted by the objective makes with the principal axis, then MO is equal to h' by h and tan theta is equal to h by FO, which is also equal to h' by L. From these two equations, we get MO is equal to L by FO. Let this be equation 7. If the eyepiece is adjusted in such a way that the image A'-B' is formed between the first focus FE and the optic center of the eyepiece, and it is very close to FE, then the final image is formed at far point. Then we say that the compound microscope is set in normal adjustment. Since the eyepiece acts as a simple microscope, using equation 3, we can write the magnification due to eyepiece ME is equal to D by FE. Let this be equation 8. Since the image formed by the first lens becomes the object for the second lens, the total magnification of the combination M is the product of the magnification due to the objective and the magnification due to the eyepiece. Therefore, M is equal to MO into ME. Substituting the values of MO and ME from equations 7 and 8, we get M is equal to L by FO into D by FE. That means, when set for normal adjustment, the magnifying power of a compound microscope M is equal to L by FO into D by FE. If the eyepiece is adjusted such that the final image is formed at the near point, then, using equation 6, ME is equal to 1 plus D by FE. In such a case, the magnifying power of the compound microscope M is equal to L by FO into 1 plus D by FE. For larger magnification, the objective and the eyepiece of a compound microscope must have small focal lengths. The magnifying power is generally expressed in terms of x, where x is the number of times the size of the image appears to be when compared to the size of the object. For example, if a compound microscope is marked as 10x, then its magnification is 10, and It denotes the number of times the size of the image appears to be when compared to the size of the object. In fact, the objective and the eyepiece of a compound microscope are made of a multiple lens system. This improves the quality of the image and minimizes various optical defects.